Hello everybody! I love properties of exponents and I hope you will too. Notice here we have a blank piece of paper. So because not all of us have access to printers, we have notes that you can just take down by hand. Now I know some of us like to print that off, so if your teacher has that available for you, that is also excellent. But I wanted to take this time to show you a way of doing it just off of a blank scratch piece of paper. Now, if you were doing it with the notes that are printed, it may look something like this, but this is not very squishy. So what I'd like to do is do these notes landscape style, so side to side. Now, we're going to start by looking at the essential question. I'll write that up at the top as a normal paper, but then we're going to work long ways because there's a lot to write. So, this is 6.1. Properties of exponents. And our essential question is, how can learning exponent rules make my life easier? Okay, you can see I went ahead and just wrote that out. I hope you're pausing this and writing as you need to, but I don't necessarily want to take up your time doing it all while you're watching, although I will do a fair amount of it that way. Now, how can make your life easier? Some things you're learning new things, just new stuff to do. However, exponent rules, they're all based off of the idea of what an exponent is, and it's really just about making shortcuts, making things easier when you need to simplify problems. Okay, so there are a few things that I think that we should look at as far as objectives go. So, one, let me pause. Alright, so for our objectives, one, we want to just become familiar with those exponent rules. Then, we want to simplify exponent expressions using a reference, for example, using our note that we'll fill in. And then three, this is what we eventually want to get to, simplify exponent expressions. If you haven't seen the shorthand, I want you to see it. So if I do this, it means essentially ditto what was right there. So simplify exponent expressions by instinct. So I want this to come to the point where you're just kind of doing it by feel. Alright, now we're going to switch this sideways so we can maximize our side-to-side space use. Now, if you are using these, we're going to write something up above here because this is sort of the basis of where it all comes from. So exponents are simply repeated multiplication. So that means that if I have a to the first power, that's just a, because it's telling me that anything to the first power is itself. And we also know things like 3 squared. Well, we're very comfortable with squaring things because we've had to do that for a long time. And so that just means that it's this number multiplied by itself twice. So that's 3 times 3 equals 9. So that's simply the definition of what an exponent is. It tells you how many times you multiply something by itself. That's not what we're learning today. That's all background. What we're learning today is how to use these basic ideas, the definitions, to simplify bigger, more complex numbers and variables. So this is essentially what we already know. And then we're going to look at sort of 3 general ways of seeing these rules. We're breaking them down into about 7 rules. We're going to look at what the rules look like. We're going to look at where do the rules come from. If you're using the printable notes, that's the meaning. So it's where do the rules come from, and then we're also going to look at how and when do we use them, which would be under examples. So what do they look like? Where do they come from? How do we use them? why / where do they come from, and how do we use them? So we're going to go through each of these rules in succession. So I'm going to do all the rules, 1 through 7, and then I'm going to go back through those same rules and talk about where they each come from. Then I'm going to go back through them again and do an example. So instead of just going rule number 1, boom, 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 rule number 2, boom, 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 I'm going to go through all the rules like this, and this. This is sort of a cyclical way of looking at it. So each time we look at it, I hope you gain a deeper understanding of that specific rule. Okay, so first we have a to the 0 equals 1. Then we have a to the m times a to the n. Remember, we can show multiplication using parentheses, but we don't have to. Equals a to the m plus n. A to the m divided by a to the n equals a to the m minus. So notice when we multiply, we add. When we divide, we subtract, which kind of makes sense, right? So multiplying and adding all make things bigger, and dividing and subtracting all make things smaller. Remember, multiplying and adding, bigger, dividing, subtracting, smaller. Then we have a to the m, looks a little messy, to the n. So we have a power to a power, multiply the powers. So that's m times n. Remember, whenever you have variables squished together, we assume that they're being multiplied. Now, this next rule is exactly the same as this rule, but I'm showing it to you again in a different circumstance. So let's say a to the m, b to the n, to the p. Well, this is this exact same rule here, except now we are distributing. So that's going to give us a to the mp and b to the np. So if you take a little look here, that's distributing. See, on an individual scale, it's just like this one, right? Power to a power, multiply the powers. This next one is that same rule again, just looking at it with a fraction. A to the m, b to the n, all to the power of p, equals a to the m p over b to the n p. And then at the bottom, we have one rule which we're going to look at in two different ways, kind of like we looked at this rule in multiple ways. So it's that negative powers, the little negative is like a ticket to get the whole exponent across the fraction bar. So a to the negative m equals 1 over a to the m. That negative power, the negative is just a ticket. You give it to your conductor, they take you across the line, across this fraction bar line, and then you get to the other side. You're still there completely, except that you gave up your ticket. And so that is both from this way, and then also just to remind you that it goes both ways. You can also look at it like this, a to the negative m, it also goes up. So it doesn't matter which side of the tracks you're on. You use your ticket, you cross across that fraction bar, you get to the other side. Make sure you have all of this written down. Now, as I said, we're going to layer through this. So we've looked at the basics of this is just what they look like. Then we're going to go through what they look like using numbers instead of letters. Then we're going to go through, etc., etc. So, pause if you need to pause, but we're going to keep on going. because I'm assuming that you know when to pause. Okay, so this would be, for example, if we did 3 to the 0 power, that equals 1. This would be, for example, if we did 2 cubed times 2 squared, that's 2 to the 3 plus 2, which does equal 2 to the 5, which is 128, in case you were wondering. Then for this one, if we wanted to look at it with numbers, so we have 5 to the 4th over 5 to the 2nd. We'll use our property, so that's 5 to the 4 minus 2. It's 5 squared, which is 25. Down here, we have 4 squared cubed. So that would be 4 to the 2 times 3, which is 4 to the 6th, which is a big number, 4,096. This one, I'm giving you a specific example. This example I'm putting down here is thinking back to when we had our factoring of cubics, right? So we had to figure out what the cube root of something was, and then we had to square it for some of the terms, and we had some struggles with that. So I am showing it to you here. So we distribute this. So that's going to be negative 3 squared times x squared, which is going to be negative 3 squared is 9, x squared is just x squared. Then we have here, let's do 2/3 squared, which is 2 squared over 3 squared, which is 4/9. Down here, we have 7 to the negative 2. We use this negative as our ticket to cross that fraction bar. So we're at the top, so now we go to the bottom. But we can still simplify that. And we're just going to look at that in reverse right here. So say we have 1 over 7 to the negative 2. Okay, that negative is simply our ticket across the fraction bar. We use our ticket, so we get across, we keep that squared. It's just not negative anymore because we used our ticket. And that's going to give us 49. Okay, so this is the rule using variables. That's the official way. Here's just demonstrating the rule very simply with numbers. Now we're going to look at, where these rules come from, the meaning, why we have them, where they came from, and then we'll do slightly more complicated examples. Okay, so I'm going to do sort of the meaning in blue. Okay, so I actually want to start, I'm going to start here with this rule, because this rule I think is kind of the basis for everything. So we're going to actually start here. I'll skip around just a little bit. So we're going to have, let me see what, don't want to use too big of numbers because that can get really messy. Okay, so if we have a to the 3rd times a to the 4th, Okay, going back to what we already know, that an exponent power tells you how many times you multiply the base number, 3 being the base, or the base variable, a being the base there, how many times you multiply it by itself. We're going to zoom in a little bit. So that means that this is essentially a cubed is a multiplied by 3 times, and 2, 3, 4. Okay, so we've got a cubed times a to the 4th. That is just, if we want to then, we accordioned it out. Now if we want to bring it back together again, we can say that this is a to the 1, 2, 3, 4, 5, 6, 7. So we can accordion it out and then condense it, or if we just want to use our exponent rules, we can go, oh, this is to the 3 plus 4, which equals RA to the 7th. Now we're going to do this next rule, because this next rule focuses on those same foundational principles once again. So where does this one come from? Say we have a to the 6th over a squared. That's 1, 2, 3, 4, 5, 6 over 1, 2. So remember, anytime we have numbers divided by themselves, they give us 1, right? So 3 divided by 3 is 1, right? It cancels. So here we can cancel top to bottom, cancel top to bottom. There's nothing else to cancel on the bottom. We just have this left on the top. So that's going to be a to the 1, 2, 3, 4, a to the 4th. Everything canceled on the bottom, so that would just be divided by 1, which we don't need to write because that's unnecessary. And instead of expanding this all out, we could have just said, okay, I know by my property of exponents that 6 minus 2, that. I hope you can see that while you can multiply these out, and I hope you do when you're just learning it, that you wouldn't want to have to extend this out, cross-cancel them out, and combine them back again if our numbers were like 600 and 321. We would want to use our properties because we can do 6 minus 2 much better than we can keep track of writing all those little letters or numbers. Okay, so with this in mind, we're actually going to go back up to this rule number 1 now. So this is saying that anything to the 0 power equals 1. And what that will look like for us, for example, say that we have a to the 7 divided by a to the 7. Okay, so I'm just showing you where this rule comes from. So we can say that's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, over 1, 2, 3, 4, 5, 6, 7. We can cancel out. Since they're the same number, they all cancel with each other, which just leaves us 1. Or we can use this property that we just practiced down here, which is why I did this property before this one. So we can see that this would be a to the 7 minus 7 using this rule, right? Whenever we have division, we subtract the powers. So division, we subtract the powers. That would give us our a to the 0 power. Ah, that's how we get a weird little 0 there. And that just gives us that. So that's telling us where we got this rule. Okay, next, we're going to skip back down to here. So we have, say we have a to the 4th squared. Now remember, An exponent power tells us how many times we're multiplying the base by itself. So, here this power is going, this power is going to that base. So that means I'm going to multiply this by itself twice. So it's going to be a to the fourth times a to the fourth. Now I'm going to expand this out, which is going to be a little annoying. So 1, 2, 3, 4, a to the fourth times 1, 2, 3, 4, a to the fourth. I could bother doing another step showing you how I just remove these parentheses. Yeah, I'll do it. This is actually a good review because a lot of us are still a little bit uncomfortable with when we get rid of parentheses and when we don't. But this is all multiplication anyway. And if we combine these, 1, 2, 3, 4, 5, 6, 7, 8, this gives us a to the 8th. Or we could know from our property that power to a power multiply the powers. So this is going to be a 4 times 2. See, we multiplied, which gives us a to the 8th. This one right here, since these are the same as this rule, these are going to look very similar. So I'm going to go through these two very quickly because it's the same meaning, the same reason where they came from as this one. They all are. So let's just use that same example. So I use this here. Here, we showed it to you as distributing, right? The 2 went to the number and to each variable that it has. Here, I'm showing how we do it this way, right? Just going back to the definition. All of this meaning, all of this blue is just showing the definition of exponents, saying that an exponent tells you how many times you multiply the base by itself. Okay, and so then once we'd have this, then we would go ahead and combine our negative, well, actually I'll just combine it all together in one step. So negative 3 times negative 3, which would be positive 9, and then x times x, which would be x squared. Which is the same thing that we did here. Okay. Let's do just the power of 2. We don't want our powers to get too insanely big. So remember, exponent just tells you, the power just tells you how many times you multiply a thing, specifically in math terms, the base by itself. So this whole thing is to the power of 2. That means I'm multiplying this whole thing to itself 2 times. And once again, back to the definition of exponents. 2, 3, 4 for that one. 1, 2, 3, 4 for that one. I need to make my fraction bar longer so everything is contained. And this is, let's see, e to the 6th over a to the 8th. Or we can just see that a to the 3 times 2 and a to the 4 times 2. 3 times 2, 6. 4 times 2, 8. And yes, this can be simplified further, right? If we wanted to go ahead and do that, it would be, and we could cancel it out and whatnot, but it would be 1 over a squared, in case you're curious. Okay, I'm going to draw a little arrow to give a little bit more space between these examples. Let's actually show this whole thing in view. So whenever we have a negative attached to our number, the negative just means that you have a ticket to cross the fraction bar. So where does that rule come from? Well, we have to backtrack a little bit to see where that rule comes from. So let's say we've got a to the 9th power and a to the 11th. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You need to make this longer. Start canceling. 1, 2, 3, 4. Let me actually cancel in a different color so it's easier to follow. 1, 2. Okay. Wait, did I line that up correctly? See, this is why we don't want to do it like this, because now I need to recount my numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh! That's where we get off. 11. Okay. Now, all is canceled out on the top. We still have 2 a's on the bottom. So that is 1 over those 2 a's. Which is simply when we divide, looking back up to this rule, when we divide, we subtract the powers. So 9 minus 11, which is -2. And last but not least, it's the same thing again. So, actually, let me just write 2 things. Same as above. For your example, please take a moment, make sure you have everything copied down that you need to have copied down. And just note negative powers, the negative is the ticket to cross the fraction bar.